Degasification methods. Following are the different methods of degassing: flushing, vacuum degassing, static bar treatment, induction degassing, steam stream droplet degassing, fractional degassing. Flushing. Flushing or gas scavenging with an inert gas is one of the most effective methods of extracting dissolved gases from the molten metal. Inert gases such as chlorine, nitrogen, helium, or argon are used in practice for degassing non-ferrous metals, while carbon monoxide is used for ferrous metals and nickel-based alloys. Figure illustrates the principle of flushing with inert gas. In this method, the inert gas is simply piped from storage tanks through graphite tubes directly into the liquid metal. The piping of inert gas creates bubbles which move upwards, and any dissolved gas in the liquid metal migrates readily to the bubble where it collects and is flushed from the melt into the atmosphere. The rate of degassing depends on the rate at which the gas diffuses into the gas bubbles. For ferrous metals and nickel-based alloys, nitrogen cannot be used as inert gas. They form nitrides that affect the grain size. An inert gas, also called as noble gas, is a gas which does not undergo any chemical reactions when allowed to react with many substances. Purified nitrogen and argon gases are widely used as inert gases due to their availability and low cost. Inert gases are generally used in those applications in order to avoid unwanted chemical reactions, especially oxidation and hydrolysis reactions with the oxygen. Vacuum degassing. As the name suggests, vacuum degassing is a technique of removing dissolved gas from the liquid metal by lowering the pressure inside the vessel containing the liquid metal in the presence of vacuum. It is particularly used in steel foundries for degassing hydrogen and oxygen from liquid steel. Steels refined in vacuum are characterized by homogeneous structure, low content of non-metallic inclusions, and low gas porosity. Vacuum degassing is typically performed in a specially designed chamber or vessel known as vacuum degasser. There are a number of variants followed in the vacuum degassing process. However, working on the same principle by exposing the molten metal to a low pressure environment, the reduced pressure inside the vessel or chamber causes the dissolved gas to become less soluble and separate from the liquid melt. When the vacuum degassing process is complete, the gas is removed from the vessel and the pressure is returned to normal. It must be noted that the effectiveness of any vacuum degassing operation depends upon the surface area of liquid melt that is exposed to low pressure. Hydrogen removal is a diffusion and partial pressure phenomenon, while oxygen removal is a function of chemical reaction of oxygen with carbon and the partial pressure of carbon monoxide. The different variants of vacuum degassing with respect to hydrogen gas removal are discussed as follows. Static bath degassing technique diagram. Static bath degassing. Static bath technique is the simplest form of degassing technique wherein ladle tapped with molten metal is placed within a chamber, sealed and evacuated as shown. The process, although time consuming and requiring additional requirements, may be simplified by sealing the tapped ladle itself with a cover as shown in figure. The space above the molten metal in the ladle forms the vacuum chamber. The reduced pressure inside the chamber causes the dissolved gas to become less soluble and separate from the liquid melt. Once the degassing process is completed, the pouring of metal is carried out. This system gives the advantage of a small pump down volume, reducing the vacuum pump's capacity requirement. However, since the system does not utilize any circulation of the melt other than that provided by the natural convection, degassing proceeds at a slower rate. Induction degassing. Induction degassing technique overcomes the disadvantages of static bath technique. The system as shown in figure consists of a crucible surrounded by induction heating coil. The entire assembly located within a chamber that can be sealed and rapidly evacuated. Molten metal is transferred from the melting unit into the crucible, wherein the current flowing through The coils create a magnetic field that induces eddy currents and circular electric currents, producing a stirring action within the molten metal. The bath agitation, which takes place at normal frequency, is just sufficient for hydrogen gas removal from the melt to take place. The effect of removing dissolved gas is enhanced to a greater extent in the presence of vacuum atmosphere. Vacuum degassing process is more efficient, except cost of furnace being a major drawback. However, foundries operating with induction furnaces have the advantage, since all the operations like melting metal under vacuum, refining, degassing, heating, alloying, etc. are done in a single unit melting furnace. The process is relatively flexible, featuring the independent control of time, temperature, pressure, and mass transport through melt stirring. Stream droplet degassing. In stream degassing technique, the molten metal from the ladle is poured down into another preheated ladle placed in an evacuated chamber as shown in figure. Bottom pouring of molten metal is desirable as it creates a stream of flow into the vacuum chamber. The sudden exposure of liquid stream in the vacuum chamber leads to very rapid degassing due to the increased surface area created by the breakup of stream into droplets. The process helps the hydrogen gas dissolved in steel to be evacuated by a vacuum pump. The major amount of degassing occurs during the fall of liquid stream, and as such, the height of the pouring stream forms an important design parameter in the process. Fractional degassing. In fractional degassing technique, the molten metal to be tapped in the ladle is progressively degassed by treatment of fractions of the metal in a separate pump metal vacuum vessel as shown in figure. The system makes use of two tubes connected at the bottom of the vacuum chamber, with one of the tubes argon connected to a pipe supplying argon gas through its refractory lining. Both the tubes are immersed into the ladle containing molten metal. With such an arrangement, the liquid metal flows up into the vacuum chamber under the influence of inert gas bubbles bled into the base of the tube. The figure showing fractional degassing level of the molten metal in the vacuum chamber is determined by the atmospheric pressure. Through the second tube in the vacuum chamber, the molten metal flows down back to the ladle, producing continuous circulation of the melt and resulting in the removal of gases. Fettling and cleaning is carried out following the shakeout, removal of casting from sand mold, and knockout, removal of sand core from casting operations. Fettling includes the following steps: removal of sand and other impurities. The rough casting removes from the mold consists of adhering molding sand, core sand, oxides, and scale, which has to be cleaned. This is achieved manually, mechanically, or by chemical means. Wire brush, files, and other tools are used in manual operations, while air blasting, hydroblasting, tumbling, etc. are a few equipments used in mechanical operations. Chemical cleaning methods utilize baths of molten caustic soda containing additional reagents to react with and break the surface oxide layer. This loosens adhering sand also. Removal of excess metal. This step includes removing excess metal such as fins, blisters, and stumps of gates and risers and other unwanted projections from the castings. This is achieved by chipping, sawing, flame cutting, grinding, and other operations. Finishing of castings. Finishing is carried out to smoothen parts of the casting where gates and risers were attached, and also improve the surface finish and appearance of the casting. Different finishing operations like grinding, polishing, buffing, etc. are used for the purpose.